Start recording. Okay, so I'm actually start. Go. All right. So today is going to be fun. Although I mean, one of the inconveniences about like having to delay this is that delay the exam is that basically some of the stuff that we're learning today and a lot of the stuff that we're going to be learning on Monday is actually going to be on your exam, the first exam. Just because that would be way too freaking much. So I'm going to do my best to not keep it too stale on Monday. On Monday, what we're going to have is on Monday we're going to use we're going to go over the recursive data structures. In other words, we're going to go over linked list again, but we're going to look at it from a recursive perspective. No. Let's see. Let's look at. Okay, so it's Kaufman, and we're going to look at Chapter 5 PowerPoints. And then we're going to go ahead and create the class in the Recursion package. So give me 1 second. I need to duplicate the display. So it's extending it. There we go. Duplicate it, and we're going to call this Recursion Examples. Okay. So, if I was to put a title on each third of the class, like each third of the 15 weeks, the first week would be about memory locations, right? Because we're learning to work with memory locations, and understand how references work, and make sure basically it's building up the finesse you need. I would call this segment basically recursion, because that's what this is. Because we're going to be learning about recursion, then we're going to be going into trees, which you could program without recursion, sure, but it's a heck of a lot harder. And if you do it with recursion, then it's easy. Like on the second exam, I typically ask a couple questions where I give you the entire page to write your answer. You know if you've learned how to do recursion, it will take you about maybe 4 or 5 lines max, and that includes the if statements and the line that includes the curly braces. So recursion makes everything really easy to program if you can figure out how to do it recursively. There are some drawbacks to recursion, as we'll learn, and sometimes it's not perfect. And it's also a completely unnecessary feature. Anything you can do with recursion is something you can do with links. But recursion is often easier to read. So, but it's a tool, right? And the idea here is that basically it's the whole old saying of if you have a hammer, then everything looks like a nail. Here I'm teaching you how to use something else, maybe a power drill, essentially, right? You had a hammer, now I'm teaching you how to use a power drill, okay? And so that you'll have another tool to approach problems in a different manner. It may not be the best problem for everything, but it is the best problem for a lot of things, or it's the best solution for a lot of things, and it will help you basically think in a lot of different manners. So we're going to learn how to think recursively, okay? How to be able to build up a recursive method. So how do recursive methods actually look? Did I remember to take the pen? Uh-oh. Okay. How to start, how we write recursive algorithms, and we're also going to learn the search algorithm, so how to efficiently search arrays. We're going to learn about recursive data structures. Specifically, we're going to learn a different way to think about and build a linked list, which is recursively. We're going to also now actually get into really some fun problems. I mean, as if mazes weren't fun enough. We're going to learn how to solve some basic problems in chess, like the 8 queens problem. So not actually like playing a game of chess, but like solving problems that involve chess pieces. Like, so if anybody has played chess, then this will be stuff like, well, one of the classic problems we'll be going over is the 8 queens problem, or the knight's tour problem. And if you haven't played chess, it's going to be fairly easy to understand how this works, because you don't have to know all about the chess rules. You just need to know how do pieces move. We'll skip the 2-dimensional processing, but we're also going to learn how backtracking works in general, because recursive backtracking is one of the greatest tools out there for solving problems, because you can use it to solve mazes, which we're already, when you're doing, the way you're supposed to use stacks, if for the maze problem, you're using it to do recursive backtracking without actually using recursion. Because if you're doing recursion, you're basically using a stack, as you'll see. So we can solve a lot of programming problems that are difficult to conceptualize and solve linearly. In other words, that if it's hard to think about, sometimes it's easier to think about it recursively rather than writing a loop. Like, I don't really know how I would solve a problem, a tree problem, without using recursion or a stack. So in the field of AI, recursion is typically used to do things like playing the full game of chess or proving some math theorem or recognizing some patterns, which is huge. So we can do all sorts of things with recursive algorithms. And the idea here is that actually we are getting into the whole Russian nesting doll idea. And the idea here is that inside every Russian nesting doll is a smaller, slightly simpler doll, right? The outer doll is the most complex, but once you open it up, it gets you get the smaller, simpler doll. And that doll has inside of it an even smaller and simpler doll, and so on and so forth. As you open up the Russian nesting doll, the dolls become simpler. So we're going to start out with actually a mathematical theorem on the board. No, I haven't switched yet. I was looking for a marker, making sure that I had one. We're going to start out with something with some math on the board. Just making sure. No, really, is it not switching right now? Automatic scene switcher. Oh, there it switched finally. Okay. And then switching back, now switch again. Okay, so let's go ahead and start by looking at what we've got here. So this is the most basic recursive problem I can come up with, which is 5 factorial. Okay, 5 factorial. So for refresher, 5 factorial means we're going to be multiplying 5. That's equal to 5 times 4 times 3 times 2 times 1. I don't suppose anybody has a better marker. Dry erase marker. Promise I'll give it back. Because I had one with me and I left it in the other room. Okay. Okay. 5 times 3 times 4. Okay. And we can create a function that solves this iteratively, right? We could totally write something along the lines of, and I'll be using this again, so don't worry, didn't just take it for no reason. Public, static, long, I'm going to have the factorial function return a long because it gets big really quickly. Int n, right, since we're multiplying, so this is 5 times, so this is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So 4 int n is equal to, int I is equal to n, I is greater than 1, I minus minus, and this is going to be a running product, so we do int product. So with a running sum, you start with 0. With a running sum, you start with 0 because you keep adding stuff to it. The running product, you're going to start with 1 because if you multiply, if it started at 0, we'd be multiplying against 0, right? And that would end up with just, 0. For some 0, for adding, 0 is the identity, and here 1 is the identity. So return product, and now we do product times equals I. Not the easiest thing in the world to read, right? Because we've got a loop, it's going in reverse, which always makes you have to stop and think, right? For a second, how many times it's going to run, right? Does it include we need to include the 1. Oh, right, so it's not as easy to write, right? So you got to remember to do the equal sign to make it work, right? And this will calculate 5 factorial. So sometimes doing it with a loop, even if it's simple, you do have to stop and think, right? But with recursive functions, we can actually, and recursive definitions, we can actually, change this up a bit. And the idea behind recursion, the way I like to put it, is that we're being really freaking lazy. Okay? So the idea behind recursion is that we're going to break this problem up into smaller problems, right? And the key insight here is that when we say 5 is equal to 5 times 4 times 3 times 2 times 1. The key insight here is that this section of the problem, 4 times 3 times 2 times 1, that's 4 factorial. Okay? And at 3 times 2 times 1, that's 3 factorial. And then 2 times 1 is 2 factorial, and 1 is 1 factorial. And anybody know what 0 factorial is? 1. I don't know why. Anybody know why? What?
I think it's just this thing.
Just one of those things? Okay. So, right? And you can tell this is in the math class because that seems like something that you should know. But, so the idea here is that I'm going to be lazy. What I'm going to do is that if I'm going to compute 5 factorial, what I'll do is that to compute that, I'll return 5 times whatever 4 factorial is. So now I'm going to go and do 5 and solve the simpler problem of figuring out what is 4 factorial because that's simpler, right? 4 factorial, I'll solve that by multiplying 4 times the even simpler 3 factorial. 3 will be multiplied against 2. Sorry, 3 will be multiplied against 2 factorial. I'm running out of space here because I'm terrible at spacing. So, and then 2 will be multiplied against 1 factorial. And I think once we get to 1 factorial, we can kind of just stop and say, if I'm trying to figure out what 1 factorial is, I'll return 1. Okay. So now we know that 1 factorial is 1. So what I can do is that I can replace 1 factorial with 1. Then 2 times 1 is equal to 2. So I return 2 here. 3 times 2 is 6. So I return 6 here. 4 times 6 is 24. So 24 times 5 is 120. So now I return 120 as my answer over here. So before we dive into the code, let's just write this mathematical definition, this recursive mathematical definition on the board. Because if you've... so first we need to realize 2 things. A recursive definition needs 2 parts to it. First, it actually needs a recursive part to it, which is that basically we can break the problem into a simpler problem. So we can take factorial and break it down to, n times n minus 1 factorial, right? So we can say each factorial is made up of actually a slightly smaller factorial. Okay. And the other thing is that we need to know when to stop. We've got to have something called n, so equal to 1 when n is equal to 0 or n is equal to 1, right? That's our base case. If n is 1 or 0, we know that. So if we get n factorial and it was 1 factorial, 0 factorial, we're just going to return 1. Otherwise, the definition is n times n minus 1 factorial, or n greater than 1. Okay? So let's go ahead and convert this into some code. Let's go ahead and delete what we have here. Okay? And write what we have up there. So it just takes a bit of translation. So if n is equal to 0 or n is equal to 1, we just return 1, right? And the reason this is because if the idea here is that that basically the base case here, what we have in the base case, what we mean by the base case is that it's something so simple that we can just return a value. We don't even have to think about it. We don't really even have to compute anything. If n is 0 or n is 1, return 1. That's what a base case is. And here's the recursive case. So all recursive problems are basically just, you have to figure out 2 things. What's the base case? What's the recursive case? So here's the recursive case. Otherwise, we return n times, right, what's up there, which is n times n, factorial of n minus 1. So the key thing about what recursive functions do is that they call themselves, right? So you can see that this function calls that factorial calls factorial, and it will keep calling factorial until it gets to a base case. So it's important to note that just because a function calls itself doesn't mean it's recursive. Public static void not recursion system.out.println. This is not recursion, right? And this is not like this is not a pipe kind of thing. This is actually not recursion over here. If I do this, not recursion, okay? What happens when I run this? Infinite loop? Stack Overflow is the correct answer. I would also, in theory, it's an infinite loop. In practice, it's what we call a Stack Overflow error. So exception in thread main at Stack Overflow error. So you've probably heard this term before, if for no other reason than you Google stuff. But let's just so we understand what a stack is now, right? So an overflow means maybe we had a stack with a limited amount of space, and then we tried to push one too many things into there. What we were trying to push into there was one too many activation frames. In other words, what we'll see, what the slides will show us is that we basically try our best to push as many things onto this activation frame as onto the stack as possible. And if when we're done with the method call, we pop off the stack to figure out where we came from. Okay, so we use a stack to keep track of what method we're in. Yes?
You mentioned Google. Fun facts. If you type recursion into Google,
it comes up with recursion.
Yes.
So yeah, it's one of those nice things. I personally like the Wikipedia page on recursion because we've seen recursion with, right? So did you mean recursion? But recursive art is actually one of the best examples of recursion. So, which is one of those Russian nesting dolls. So here, right? And you can see she's holding a picture of herself, which is holding an even smaller picture of herself. And at that point, it loses detail. But the idea here is like a fractal in the sense that it would go forever, except that's not actually what fractals do. So, or the Sierpinski triangle, right? Where basically each triangle is made up of three smaller triangles of itself. So you can see basically how each triangle is made up of three smaller of those triangles. So there's a lot of cool art that you can do with recursion, and of course the Russian nesting dolls. Okay, so let's go and see how deep this went, though. By the way, this time we're going to add an argument. Still not recursion. Int n system.out.println. This is not recursion plus n. N plus 1. Right? Even now that we're passing in an argument and that argument's changing, this still isn't recursion. Let's see how far we got. We got about 8,000 method calls deep, about 8,100 method calls deep. Okay? So why is this still not recursion? Well, for it to validly be recursion, you always have to get, each call has to make progress to the base case. First off, this doesn't make progress towards any base case because it doesn't have one, right? So for it to be valid, we'd have to have a base case, and every time we do a recursive call, we'd have to make progress towards the base case. So now let's check out how factorial works. So system.out.println factorial 5, right? And the idea here is, we run this, it'll give me 120. It's going to give me 120 and not some other weird number because it's going to do 5. So we pass in 5. It calls 5 times 4 factorial, which returns 4 times 3 factorial, and that 3 factorial returns 3 times 2 factorial, and 2 factorial returns 2 times 1 factorial, and 1 factorial returns 1, which means that the 2 factorial returns 2, which means the 3 factorial returns 6, which means the 4 factorial returns 24, which means the 5 factorial returns a grand total of 120. Right, which is, and the only reason I was able to do that off the top of my head is because I've done this example a million times, and it was on top of the board. It's not because I'm actually smart or anything like that. I'm not. I'm just, practice makes perfect is literally what's going on over here. So now, so let's go ahead, and again, these factorials, they go up crazy fast. Yes?
I noticed when I put in like a high number like factorial 40, the result comes out like negative.
Ah, that's because, again, of overflow. That means that notice how basically, so let's go ahead and print out the biggest long. So system.out.println long, so the long class dot max value. So the biggest long there is this number, right? And at some point, and factorial 40 is actually much bigger than that number, right? If I needed to deal with this, I would actually turn it in. If I really wanted that, I should probably really be dealing with big integer. So if n, so now it would be return 1, otherwise return factorial of b, should probably be now factorial of n dot multiply times another big integer, which I'm going to be, let's see, yep, n, new big integer, let's see, does that work? I don't rarely work with big integers. Constructor big integer long is not visible. Oof. I always forget how to work with big integers, which is the class for what you need to use when you've got things that are too big for you to use. But why? But going back to your original question, because I don't want to waste too much time on trying to figure out how to make it correct, which is why does this happen? Well, it's because of overflow. It's the way numbers are represented in binary. You've got 64 bits, right, to represent a number. The first bit is used for positive and negative. The second bit is used for, and the rest of the bits are used for giving me a value. And negative numbers are represented as by inverting the positive number, so flipping all the bits and adding 1. So what happens over here is that when you try to add a number that's too big, that's so big that it can't be held, it flips over, it goes around the other way. Essentially, just so remember, because that firstmost bit is for negative numbers. I bet you if you increase it to like 41. I was thinking that would be positive. I'm trying to remember where these things, where it's going to come back. It should come back around positive at some point. But the idea here is that you're overflowing your values. They're too big for even a long to hold. Okay, so factorials go up really, really, really quickly, which is why basically a factorial time algorithm like Bogosort is terrible. Okay, let's go ahead and look at some other problems. So the idea here for designing a recursive algorithm is that you've got to have at least one base case, something that's super simple that we can just say the answer without thinking about it. And then we can, you can solve it recursively if you can take that problem and reduce it to smaller versions of the same problem. Okay, and then finally the last thing is that all those you've got to be able to take all those smaller problems and combine them into the full solution. So we're going to look at some stupid recursion methods, some of which are stupid because they're just unnecessary, but they're good for actually learning how to think recursively. So say you want to find the length of a string recursively. Okay, well, let's think about it. If the string is empty, in other words, it has no characters, then the length is 0. Otherwise, the length of the string is 1 plus all the characters after from the second character onward. So in coding terms, this would be public static int length of some string. If the string doesn't exist, return 0. Otherwise, it's 1 plus the length of the substring after from the first character onward, right? So we count 1 for the first character, and then we count the rest. How long does this algorithm take, by the way? Not n squared meaning would be that basically we count each letter n times. So it's not n squared. It's n, because we count each letter once, right? We do n function calls, right? So this returns like the string. So this is, congratulations, we somehow written a linear time algorithm for counting the length of a string. We could have done it in constant time just by calling dot length. So, okay, this one's actually, while it's stupid, it actually doesn't take too much longer, and it's cool enough that I'm actually going to rip it out here, which is basically, this is a recursive algorithm for printing each character one line at a time. So totally control line. So it's a public static void print characters, and all it does is just print each character one at a time, right, on a line one at a time. First thing, notice that's void, but we've got a return statement in here. Remember, when you hit a return statement, it just stops the program, whether it be return X or, in this case, since it's void, we aren't returning anything, right? So you can kind of, when you're in a void method, you can kind of use a return as like a break statement that stops the entire method, right? So see, if you hit here, you're just going to stop and just skip. I mean, it's actually completely unnecessary because you could just have you could just have a blank if statement there, but it's just good to know. So if I do print cars, hello, comma, world, right? It's your standard stuff. If I do print characters that, I get hello, comma, space, world. Each of these printed at a time. And this got the same big O if you were to do it iteratively, because, right, you'd have to look at each character and print each character individually. Here, the way this is working is that if it's an empty character, if it's the base case, an empty string, we just stop and don't do anything. Otherwise, we print out the very first character, the character at index 0, and then we go and print out the, we do call this method on the rest of the string, right? The substring starting at 1. So it would be, so for if it was just hello, it would be print out H, and then it would ask me to print the characters of LO, right? And then it would be the print out in E, and then it would print out the characters of LLO, and then so on and so forth. Yes?
Why is there a space between below and like
Oh, because it's got a space.
yeah, but after the O, it looked like there was a column should. Oh, never mind.
Yep, it's just because it's vertical. That's all. It's weird because it's vertical. Okay. What's cool about this, though, is that we can actually make a pretty significant change to this, or a simple change that has significant consequences. If I cut this line and paste it up here instead, now what's going to happen? Any ideas? It says I print the rest of the characters, then I print my character. So how's that? So how's that going to render? Yeah.
It's going to start with an exclamation mark and it's going to go like.
Yeah, it's going to go backwards. It's going to go backwards now because I'm asking to print all the rest of the characters first, then print my character, and then each character is just going to do that. So H says print all the rest of the characters, then I'm going to print out H. E says print all the rest of the characters, then I'm going to print my character. So all the recursive calls happen first, and just by swapping the lines, we're able to change this into a print reverse, which is pretty nice. So you can see it's a pretty powerful tool there. Okay, so let's see. So how do we show that this thing is actually correct? How do we actually show that this works? So it's similar to a proof by induction. How many of you have taken your math concept course and learned about proof by induction? Okay. How many of you have taken both your math concept courses and they didn't teach proof by induction? They didn't teach proof by induction? I'm surprised that they don't, because that's like, if you're learning about infinite series, they teach you how to do proof by induction. Okay, so, but for those of you who don't know, proof by induction is a two-part problem. It's proving something by two parts, and it's like, always loved it because it was like cheating, essentially, which is that basically you show that it works for the base case. The classic example is something you've already seen, which is 1 plus 2 plus 3, plus n minus 1 plus n, right? This problem. And proving that this is equal to this, n times n plus 1 over 2. So first things first, we have to show that this is true for a base case, right? For some basic input. So we'll start with 1, okay? So the sum of 1 through n, which is 1 through 1, is equal to 1 times 1 plus 1 over 2. This simplifies to 2 over 2, which is 1. So 1 is equal to 1. So we proved that it works for the base case, right? Now we need to prove that if it works for some number k, it's going to work for k plus 1, right? If we assume that it's true for k, then it works for k plus 1, which means we rewrite this equation as follows. So instead of using k on n, I'm going to use k plus 1. So 1 plus 2 plus 3 ... plus k plus 1. Okay? So notice how I just, where I had an n, I put a k plus 1 instead. So that means for here, instead of having n times n plus 1, it's k plus 1 times k plus 1 plus 1, right? Remember how this was n and this was n? Well, now it's k plus 1 over 2. So the key here is that we just need to prove these two sides are equal, which sounds like it's ridiculously complicated. But remember, we're assuming that if it's true for k, we're trying to prove that it's true for k plus 1. And so now we can use our understanding of recursion to solve this, which is that we can remember, well, we assume it's true for k, so we can rewrite this equation, right? 1 plus 2 plus 3 all the way to k minus 1 to k. We already know the equation for that. That's k times k plus 1 over 2. And so now this becomes a heck of a lot simpler to solve, right? What we need to do is probably multiply these things out so that we don't have to deal with these parentheses anymore, and then we redistribute stuff to show that basically just by adding k plus 1 to this becomes this equation over here. So you just have to set the two sides equal to each other. Okay? And that's how we would solve that problem by using proof by induction. This actually like shows up, I've basically seen this on any class I've had to do a proof by induction problem. This is like typically a classic example you would be given on a test. It would be either this one or proving that 1 squared plus 2 squared plus 3 squared all the way to n squared is the other equation over 6. So that's pretty. So that's how that will work. So showing how your recursive function, the function you just wrote, is very similar. You first show that your base case, you found a base case, and that it's actually correct, right? You show that your base case is correct, right? So in our function, we show that 0 factorial works, right? We verify that the recursive case always makes progress towards the base case. Okay, so here for factorial, we have our base cases, right? Those look correct, and then we've got n times n minus 1 factorial, right? So if we are bigger than the factorial, so if we're given n and that's bigger than 0 or 1, well, n minus 1 we'll call n minus 2, which calls n minus 3, and that's eventually, just by the magic of subtraction, going to make its way down to 1 or 0. Probably 1 first, because 1 comes before 0. Okay? And then verify that basically if you solve all the smaller problems correctly, then the original problem's also solved. Well, that means that basically we're just saying that making sure that n times factorial of n minus 1, that does give you factorial of n, right? And that's all that's saying. It's just basically saying that if you solve n minus 2 factorial and multiply that by n minus 1, you're going to get n minus 1 factorial. Okay. So the only question here is, what happens if I put in a negative number? Negative 4. I get an infinite loop. I get that Stack Overflow error. Why? Right? because I'm going away from my base case. If n is equal to 0, well, -4 is not equal to -0 or 1, so we'll do -4 times the factorial of -5, which we'll call -6, which we'll call -7, and so on and so forth, right? It's never going to come towards 0. So instead, so we need some way to handle that. I don't think there's a good definition for negative factorials, so all I'm going to do is say if n is less than 0, rather than giving an error, I'll just multiply the factorial by -1. So return -1 times factorial of -1 times n. And this isn't the correct mathematical definition, but it solves the problem. So here what I'm saying is that, so if you give me -5, I'm going to turn that into +5 and solve the factorial +5, and then multiply factorial positive by -1. So I'm going to give you the negative of what that is. And this is guaranteed not to go into, this is guaranteed that I'm not going to get an infinite loop. Why? Well, because once it's positive, it's never going to run into this case again. So let's run it to show. So it gives me -24, and 5 would give me -5. There we go. Okay. So what we've been doing, by the way, what I did on the board earlier, was called tracing a recursive method. So it's the idea that basically how can we make sure that basically drawing the way the recursion works so you get a better understanding of it. Or also called unwinding it. So you unwind the recursion and then you trace it. So length of ACE is 1, right? This is the recursive length method. Is length of 1 plus the length of CE. And the length of CE is 1 plus the length of E, which is 1 plus the length of empty string, which was the base case. So that returns 0. So now you can do 1 plus 0, which will return 1 for length of E, which now we can return 1 plus 1, which is 2, so we've returned 2 for the length of CE, so we can do 1 plus 2 and return 3 for the length of ACE. That makes sense? Right? So you can unwind the recursion by basically going down in a linear fashion, just knocking off one thing at a time. So getting into your runtime stack, the idea here is that basically to do recursion, a stack is used on the back end. Okay, so you create something called a runtime stack, and typically, like in programs like C and Java, you'll have like 2 sections of memory to overly simplify everything. You have your stack, which is the stuff where you keep your program data and the instructions for the program, and then you have the heap, which is just memory that you have out there to grab at as you need, right? So in C, you grab from the heap whenever you do a malloc statement, and otherwise you're working in the stack. Here we're working in the stack anytime we set anything up. Whenever we do a new statement, we're grabbing something from the heap. So don't worry about the heap for right now. Instead, we'll focus on the stack. You have a stack, and anytime you do a method call, you store that information on what's called an activation frame. So it stores the arguments that are passed into a method, the local variables of a method, and the return address for the function that called the method. And this is important because maybe you've wondered, okay, once I go into a method, right? Once I call a method, how does the method know to go back to to this specific instruction? Well, it does so using the activation frame. Whenever you call a method, Java pushes a new activation frame onto the stack, which has where you're supposed to go back to once the method's done. So that's how it figures out where to go back to. So here, once we completely unwind the recursion, right? ACE calls ACE's input. So length of ACE, its input was ACE, and it holds the return address of the of what called it. So it calls length of CE, which has the return address of length of ACE. So make sure basically to know how to get back to this function. And says, here's the input I had. And so here's the input for E, and here's the input for length of nothing, which holds the return address of this instruction. So once we're done with this, we pop off this one and we go back to here. And we know how to jump back to here because we have the return address of this one, so we can immediately jump to that instruction. So as a result, you get too many. So if you do too many calls, right, the stack is only so big. There's only so many variables you can store, right? Your computer's not made of infinite memory. So if you do too many function calls, for my computer it was like 8,000, it just says, it just throws a fit and quits. It does a Stack Overflow exception. It says you dug too deep there. There are Balrogs here, so we are stopping the recursion. The analogy for this that they like, and I like too, is imagine you've got an office tower where each employee has where you have an employee on every level of the office tower, and they all have the same set of instructions. So the bottom part, level 1, he's given a big problem, right? Small problem to the employee on level 2 and says, hey, can you solve this slightly smaller problem for me? And he goes, and the employee on level 2 goes, okay, sure, hold on for a second. Level 2 solves his part of the problem, and he passes it to level 3, who puts him on hold. Level 3 solves his small part and takes the smaller problem and passes it to level 4, and so on and so forth till you get to the top. Now, once you get to the top, he's the base case. He goes, wow, this is an easy problem. Why did you call me all the way up over here? You know, so he solves his problem, returns his answer to level n-1. Who solves his problem, returns that to n-2, uses that data to complete his answer, pass that back to n-2, and so on and so forth. And the employee on the bottom, he gets one answer and combines it with his answer, and he's done. Right? This is kind of the idea. Right? Basically, each method calls it, and it waits for the other method calls to complete, and then finally, the person who originally called, they get an answer. Right? You don't really need to know too much about how that works. I just want you to know that's why your program sometimes crashes when you get a Stack Overflow exception. So let's go into more mathematical definitions of these recursive problems. We're really speeding along here, which is nice. So let's go and take a look at some mathematical recursive formulas. Okay, so examples are, you know, factorial, which we've already done, the power, and the greatest common divisor, which is a little bit different than the other one. So you know, they do that over here, and they pretty much wrote exactly what I wrote. So here, this is the recursive algorithm for calculating x to the nth power, and I'm just going to make it a bit simpler to read by saying, okay, if we remember that from all the way back when we learned what an exponent was, it's just a shortcut for multiplication. So if I do 2 to the 6th power, right, well, that is really 2 times 2 times 2 times 2 times 2 times 2, right? Right, 6 2's multiplied together. Right, so let's think about this recursively. 2 to the 6th power is actually 2 times 2 to the 5th power, right? 2 to the 5th power. And 2 to the 5th is really 2 times 2 to the 4th power. And so on and so forth, right? Until we get all the way to a base case. What's our base case for this problem? 2 to the 1st is a decent base case, but there's even a better one.
2 to the 0.
2 to the 0th. Why 2 to the 0th? Because anything raised to the 0th power returns 1. Don't even have to think, right? You want to do the minimum of thinking for a base case, right? I mean, mind you, you could argue that the minimum of thinking for 2 to the 1st power is you just return what was given to you, right? So there's a good argument to be made for either of those. I'm going to use 2 to the 0th because it's got a nice mathematical definition of anything raised. So x to the 0th power, right, is 1, no matter what you get. X to the nth power is x times x to the n-1. We're going to assume that this over here is just an integer. We're not dealing with, like, x to the 2.7 power, which is just ugly. Okay. What about x to the negative nth power? It's just 1 over x to the nth power over here. So we can use this to call this one. And now, mind you, I'm not going to use x's and n's because I get confused. Wait, should we have been using n and x over here? I don't know. So we're just going to use base and exponent instead as our variables. One of the things I've always thought was silly about math is that, you know, because you're working on paper so much, you're just going to use single letters for your variables, preferably from a dead alphabet, or one that's just at least non-American. So instead, what we're going to do, since we have the ability to use variables that are longer than one letter, we're going to do that. So public static double, let's call it the PAL function. It's going to take in some double base, right? And we're going to raise it to the int exponent power. So let's go ahead and go a base case. If exponent is equal to 0, base case, don't even have to think about it. If the exponent is raised to 0 is the 0th power, we return 1. If the user is trying to complicate our life by giving us a negative exponent, if exponent is less than 0, right? They're trying to complicate our life, we'll make it uncomplicated for ourselves. We're just going to return we're going to return 1.0, right, over pow base raised to the exponent power, but instead we'll do we'll make this 1 positive by multiplying it by negative 1, right? Since exponent is negative, right? Since we're in this statement, we know that exponent is negative, and if we multiply that negative exponent by negative 1, we'll get a positive exponent. So that will bring us to our last case, which is otherwise we're going to return the base times the same base raised to the nth minus 1 power, so exponent minus 1. And we know that, so if we give a negative 1, we're going to flip to the positive cases, so we don't have to worry about counting in the other direction, right? So if we're given a positive exponent, well, that will call exponent minus 1, which we'll call exponent minus 1, which we'll call exponent minus 1, and so on and so forth until exponent is 0. So these will make progress towards our base cases. So let's go ahead and see pow of 2 raised to the 5th power. That's 32, which makes sense. And if you don't trust me, powers of 10 are pretty easy. 10 to the 6th power, that means we have 6 zeros, right? So 1,000,000. And what about negative? 1,000,000th, right? That works out pretty well. So that's cool. Now let's work on one that you probably should have known, but you didn't learn in high school because they don't teach the modulo operation, even though it's bloody useful. So the recursive algorithm, and even though you know exactly how it works, because you can simply lie and say, oh, it's division, but it gives you the remainder instead, which is a total lie. It means you work in a modulo space, but effectively this is how it works. So the greatest common divisor, or denominator, as I learned it, of two numbers is the largest integer that divides both those numbers. So it's the or the greatest common factor, sometimes you might call it. So for 20, it's 15. So for 20 and 15, that gives you back 5. For 36 and 24, they're both multiples of 12, and that's the biggest number they're both multiples of, right? For 38 and 18, the biggest factor they share in common is 2, so that's 2. And 17 and 97 are both prime numbers, not to mention they're also relatively prime to each other, but they're both prime numbers. So the only thing they have in common is 1. Now, if you're like me, you probably, when you had to do these things, you solved them by brute force, right? You just simply try to figure out what the factors are for one and the factors are for other, and that took forever, but you would get the correct answer most of the time, right? So instead, we're going to use, I think it's, what is it? I always get the two confused. I think it's Euler because he's on everything. Euler's method, GCD, or is it Euclid? I think it's Euclid, actually. Euclidean algorithm, right? Right. The issue is that you've got two people who start with EU, so, right? Euclidean algorithm, right? So we're going to use this algorithm instead, which really should be taught more because named after Euclid, who first described it in his Elements, which was written over 2,300 years ago. So, you know. That's good because he does teach recursion, and I focus on other things for that. I do like file parsing and website parsing. So, and again with recursion, a lot of you will have seen recursion. Some of you it's your first time. Recursion isn't something we said we need to teach in 1068. We might be switching that up since we're changing the curriculums up a bit, but that won't affect you because now that you're in 2168, you're out of the space that's going to be affected. So for the Euclidean algorithm, it works as follows. It's very simple. It says that if your GCD is m and n, then if n is a divisor of m, then the GCD of m and m is n. Otherwise, the GCD of n is GCD n passed in as the first variable and m mod n as the second. Everybody got that? Great. So that's a pretty simple out. No, of course you don't get that. If for no other reason, then the mathematicians are stupid and they use m and n, which easily flip around as n and m, and it sounds the same. Especially if you're not a native English speaker. So that's stupid. You could also use P and Q, but I mean, if you're dyslexic, then there's just no hope there. So, you know, it's, so again, we're going to go ahead and rename this. So we're going to have two variables and we're going to give them meaningful names, right? You're given two positive integers, big and small. And big is going to be greater than small, okay? So if the small one evenly divides the big one, right? Then they have a common, then they have the greatest common factor, right? 45 and 15. If this one cleanly divides this one, we know that this is the greatest common, the greatest common factor, the greatest divisor is 15. Okay. Otherwise, we do a bit of magic here, where we say that the greatest common divisor for both of them is equal to the greatest common divisor of the small number and the big number mod by the small number, which takes some seeing to see how that works. So let's go ahead and do, let's see, I think like, let's do 20 and 15 because that one goes by pretty quickly, and then we're going to do some other examples. So I'm just going to make a table over here. Big, small, and then big, mod, small, right? Okay, so I'm just making a table over here, right? So, and let's go ahead and, sure. So we've got big, small, and big, mod, small. So let's go ahead and say 30, let's go with 20 and 15 for our first example. So does small evenly divide this number? No, it does not. So we'll calculate what big mod small is. So 20 mod 15, that gives us 5, right? 20 when divided by 15 will give you a remainder of 5. And now we go on to the next input. Is 15 evenly divisible by 5? Yes, it is, so we return 5. Okay, let's look at another one. I think they had 38 and 18 was another one. So 38, 18. So does this number cleanly divide this one? No, because the next number is 36 for this one, and so this number just can't divide it. So we calculate 36 mod 18, which is, sorry, not 36, 38 mod 18, which is, well, it would be 20, but 20 is still bigger than 18, so 20 mod 18, so it gives us 2. 18, 2, so that's bigger, so we return this. All right, let's try something else. So give me two numbers that I can, so just give me some two numbers, right? And please, you know, I guess give me numbers I can actually work with. 53 and 27. You have to do 7. 53 and 27. Okay, so if I double, so yeah, so they are relatively prime. So 53 and 27. So this won't cleanly divide this, right? Because if I multiply 27 by 2, that's going to give me 51, right? So now I have to calculate 53 mod by 27. Well, I just said that if I multiply this by 2, I'm going to get 51, 54. So that's much bigger than this. So I need to do, for some reason I did that and got, I don't know why I was thinking, okay. Okay, so this one mod this one is going to be a subtraction operation essentially. So so we get 46 and then mod, and sorry, we do 46 and then subtract 20 from that, so we get 26, right? So now 27 and 26. Does this number cleanly divide this number? No, it does not. So now we do 27 mod 26. We get 1. Okay, does 26 and we've got 26 and 1. Does this number cleanly divide this number? I would certainly hope so. 1 cleanly divides everything. Okay. So this is the Euclidean algorithm right here. their other example, let's just grab their other example over here. I think, yeah, 17 and 97. That one would go on for a while to show that basically that it's 1. So this is a recursive algorithm because it's the same. So even though it looks quite a bit different than our other ones, okay? This is even though it looks very different than the other ones, this is actually a recursive algorithm. Why? Well, we've got a base case where basically if the bigger number is divisible by the smaller number, just return the bigger number, return the smaller number, right? Otherwise, we're going to calculate. We're going to just do our calculations here, and the smaller number is going to be the first argument. It's going to be now the new big number, and the next smallest number, so the new smallest number is going to be big number mod small number, which is guaranteed to be smaller than both. Right? M mod n will get you a number smaller than n because these things are not equal, especially since these things are not equal. Well, it's guaranteed to be smaller than n. If you mod something by n, your range of numbers is 0 to n minus 1. So it's guaranteed to be smaller than n. So it's always going to make progress towards the base case, which is that n is 1. When n is 1, well, then you're guaranteed for this statement to be true. So let's go ahead and code it up. So public static int GCD of an int big and an int small. So first off, our users are likely to be jerks or incompetent or a combination of both. So they might give us a small number that is bigger. Right. What if the second argument is bigger than the first? Right. That's actually a pretty easy fix to do. We'll just flip them. So return. We'll just fix it for them. Return GCD small and big. Right. So we just flip those two. So we don't have to worry about like trying to figure out the math, make the math any more complicated. That's what's nice about recursion. You can just do a statement like that. Else if, okay, what if the big number is divisible by the small one? We do that by doing big mod small equals 0, right? If the big number mod the return small, right? If the big number is divisible by the small number, return small. Okay. Otherwise, we do this whole operation where we return the GCD of the small number and the big mod the small. GCD of 10 and 55, right? So it's going to flip those around for me and says, oh, the biggest thing they have in common is 5, right? So 121 and 11 should return 11 because that's 11 squared. 121 and 10, the biggest thing they have in common is 1. So this works fairly well, I'd say. And it's a recursive algorithm, right? It's fairly simple to use here, right? The idea here is that we could do this with iteration, okay? So first off, you can always write an iterative solution to any problem that you can solve with recursion. Recursion is a tool. It's an unnecessary tool. You don't actually need it, right? It just makes your life a heck of a lot easier. Like, we've been building houses without power drills for a while. Just having a power drill makes the job easier, okay? And you can compare them like so, like a loop repetition condition. So in other words, the middle condition of a for loop, that determines whether you're repeating the loop or exiting the loop. In recursion, you're exiting the recursion when you hit a base case. So why would you want to use recursion as opposed to iterative methods that we've been working with for a while? Well, first off, recursive algorithms, they are simpler to write a lot of the time. A recursive can be simpler to write because we've just got this list of conditions over here, and then we just simply say what we do on each condition. So it's easier to do that. It's easier to write them. It's easier to code them up. It's easier to debug them. It's easier to read them. And that last one is important. Code is read more than it is written. I'll prove it to you. I wrote this once. It got read, what, like 30 times or something? So every time I write some code, 30 people are reading it right now, right? And same when you write code yourself. When you write code, you're going to be reading it a heck of a lot more than you're, hitting the keyboard, right? So you want your code to be as easy to read as possible. Readability in code is not to be underestimated, especially when you need to come back like 2 weeks or a month later and try to know what the heck you were doing. When it's easier to write, it's also easier to debug, right? Easier to figure out what the bugs are, right? Now, there is a drawback, of course, to recursion. While they might have an equal big O notation time, typically they're slightly slower than the iterative version, because handling method calls is a bit more expensive than incrementing a counter, right? Doing a method, calling some methods, is a bit harder. But unless you're like really super optimizing your code, there's really no reason not to use recursion, because often it's the advantage of being able to easily read something and easily debug something is always an advantage of having something slightly more optimal. You really need to make sure that is something you need to do. All right. So that being said, that's for when the big O notations of times match, when they're good. When we deal with Fibonacci numbers, however, that's not the case when we try to use a purely recursive method. So let's see a case where recursion is terrible. And what's funny is that this was like the first recursive algorithm I was ever taught, and it classically is. But who here knows what the Fibonacci sequence is, right? Thanks Dan Brown, basically, because of the Da Vinci Code, it's much more well known in popular culture. Yes.
Can you take the sum previous?
Yep, that's all it is. So the Fibonacci sequence starts with 2 1s, and then we generate all the rest of the numbers by summing the rest of the previous 2 numbers. So we sum. So this one's 2, the next one is 3, the fifth Fibonacci number is 5, the sixth Fibonacci number is 8. So what's the next Fibonacci number? 13, because it's the sum of the previous 2. 21, 34, 55, and so on and so forth, right? So this is a fairly straightforward algorithm to understand. Fairly straightforward to write in math terms. Fib of the nth Fibonacci number is equal to 1 when n is equal to 1 or n is equal to 2. And the other Fibonacci number is fib of n. So otherwise, it's not, if n isn't 1 or 2, it's equal to fib of n minus 1 plus fib of n minus 2 for everything else. Okay? So let's go ahead and just directly code that up. So, because we did that for the rest, so that's obviously going to work here. Public static long, because again, these things get big quickly. Fib int n. So this is generating the nth Fibonacci number. Okay. If n is less than or equal to 2, right? Return. Somebody puts in 0, so we'll just return 1. Otherwise, if it's not 2 or 1, we want to return fib of n minus 1 plus fib of n minus 2. Let's go ahead and is 5, which is expected. 10th Fibonacci number is 55. 20th is 6 and 5. 30th is a slight bit of lag there. And now 40. Slight bit of lag there. Now let's go to 50. And don't worry, this one will actually complete in a amount of time, but it's not immediately completing. It's actually running pretty darn slow. Oh, and it is running. Let's just confirm for a second that it is running. It certainly is. In fact, the fans on my computer are starting to come on. Now, what's nice is actually I couldn't, in my previous laptop, I could only get up to like 40 or so, and then wouldn't be able to do 50. But this, new laptop's got a nice modern i7 processor, so that's nice. But even then, it still took a while to calculate this number. In fact, it took a very long time. Why? And if I tried to calculate fib of 100, by the way, we're all going to be long dead by that time. Okay. What's going on? This really doesn't seem like, yeah.
Because when you call a function recursively, it'll have to recalculate that number even if it's already calculated before.
Right. So the idea here is that it's a twofold problem. The first is that basically that on our notice for basically all these problems, we were doing one recursive method call, right? Factorial calls factorial once for each possible condition. PAL calls PAL once. GCD calls GCD once for each possible condition. Fibonacci, on the other hand, calls it twice. And not only that, each branch is calculated independently of one another. In other words, right, to calculate fib of n minus 1, I need to calculate fib of n minus 2 to do that, right? But I'm going to be recalculating it over here. So I'm essentially wasting a lot of I'm duplicating a bunch of effort. So essentially, let's see if they have a diagram for this. Right? Yep, they do. So Fibonacci 5 needs to calculate Fibonacci of 4 and Fibonacci of 3. Fibonacci 4 needs to do 3 and 2. 3 needs to do 2 and 1. 3 needs to do 2 and 1 as well, and then they stop there. So if I were to add Fibonacci of 6 over here, we'd have to copy this entire branch over onto the right side of that call. Roughly speaking, every time I go up a Fibonacci call, I double the amount of calls I need to make, roughly. That means that basically so Fibonacci, so I did a Fibonacci 50 over here. A 51 call would take roughly twice as long. Okay? When I did 40 over here, and I mentioned there was a slight delay, right? There was a slight delay there. Well, when I increased it by 10, that meant that basically it would run, when I increased this by 10, this ran 2 to the 10th times slower, which is 2 to the 10, anybody? 2 to the 8 is 256, so
24.
then 24 times. So 1,024 times slower, roughly speaking. So that's pretty bad, actually. What to do? So one thing we can do is something called tail recursion. And the idea here is that we have this method that basically has the current Fibonacci number, the previous Fibonacci number, okay, and then where we are in there. Okay, so the current Fibonacci number, the previous Fibonacci number, that's all the information you need to calculate it. And we're going to return and then as we calculate, so we're going to actually be counting up in this case. So we start it by saying our first Fibonacci numbers are 1, 0, and we need to do n iterations of this. Okay? And so what it does is that it does the current Fibonacci number plus the second plus the other Fibonacci number to generate the new one. Okay? And then it does the current Fibonacci number. So basically, it tosses this one away, moves this one to here, and takes these two and adds them together, produce the new one. And then that gets passed into the new one, which tosses the previous away, calculates this one, and then calculates these both to create your new Fibonacci number, right? Uses the previous two to generate the new one. So here's the way this looks to generate the fifth Fibonacci number, which is that starts at 0 and 1. So to generate the second Fibonacci number, it says return 114, which says 213, which says 3, 2. So why is it 1, 1 over here? Because so why does this count down? Because the method call says each here is always going to be the number from the previous call. So we put 1 here, we put 1 here, we put 2 there, and then we put 3 there. Okay. And then the first number is always equal to the sum of the two numbers that were passed in. So 1 and 0, 2, 3, and 5. So as a result, basically, we're kind of working the other way. Rather than going from the top down, we're building from the bottom up. That makes sense to everybody? Okay. This is called tail recursion or least line recursion, where basically the recursive call is the last line of the method. The arguments in the local variable really aren't saved in the. Basically, the recursive call happens basically right over here, where it happens in the method call itself. So here, again, we would stop if n is equal to 1. So that's one way to solve it. And you're going to learn more about tail recursion basically in other classes when you do this. But it's just a way to simplify this process. The other way to do this is a technique that's also applicable, which was addressing the point that you made, which was that we don't store our previous work. So the other thing we can do is memoize, as it's called, which is that let's actually save the work, and then if we don't have it, we'll use it. So what we're going to do is that instead we're going to wrap this in a, we're going to take this method and we're going to get rid of it. And instead what we're going to do is we're going to return fib_r. What I'm going to do is I'm going to use a private method for recursion over here. And it's going to do n, and it's going to pass in a new int array of size n. And this int array is going to, actually I'll do n plus 1 because that way we can use index n and don't have to deal with like 0 stuff. Okay, and the idea here is that we're going to create a private method over here that the user can't see, so they don't know how it works. But they don't need to. We just don't want them to actually accidentally do something like this. So, and this R array is going to be called fibs. So this one is going to store all the previous Fibonacci numbers. Okay? And it's going to be able to be passed between each equation. So if n is equal to, if n is equal to 1, sorry, let's see, if n is equal to less than or equal to 2, we'll do our same thing. Return 1 as our base case. Otherwise, what we're going to do here is that we're going to say, we're going to create 3 things. We'll do an int, so we'll do a long left side. So, right, and this is the n minus 1. So let's go call it n minus 1 instead. N minus 1 is equal to, and we'll create a long n minus 2. So we're going to calculate the left side and the right side, and then we're going to return n minus 1 plus n minus 2. That makes sense? We're going to calculate those things separately. If n, so let's go ahead and see. If so first off, let's go ahead and check, do we actually have an answer? If fibs of n minus 1 is not equal to 0, right? So remember, when we initialize a new array, everything gets initialized to 0. So if fibs of n minus 1 is not equal to 0, then we already know the answer. So n minus 1 is equal to fibs of n minus 1, right? Otherwise, if else we actually have to calculate it. So we're going to go ahead and do, we're going to say n minus 1 is equal to fib or n minus 1. So we'll do a recursive call over here and fibs. So we're going to pass in that array so that it has access to it. And then once we get our answer back, we say fibs of, we're going to store it, fibs of n minus 1 is equal to n minus 1. So that way, now that's stored in the array, if I've calculated a value, I can recalculate it again. Okay, and then we do the same thing for n minus 2. A bit tedious this time around. It's not elegant. The tail recursion, that's elegant. This, on the other hand, is not. But it's a way, it's another strategy. Okay? So now, let's go ahead and run it and chant, please work, please work, please work, right? So, because let's see, what am I doing a type mismatch here? Oh, right, because this is an integer, these are long, so create a new long over here. So now, fib of 50, it returned very quickly. Because what does it do? Well, it says, it does that, this whole, so now when we do this branch, right, it still does all these method calls here where 5 needs to calculate 4 and 3 to solve itself. But but here it's going to say 4 is going to solve 3 first, and then it's going to solve 2. So it returns and stores that value, and then it stores value for 3 for later use. It's already calculated fib of 2, so it's stored. So now when we go and solve fib of 3, well, instead of calculating it recursively and going down the whole branches, we just look in the array and use that. So the disadvantage here is that I'm using up some extra space, but I mean, it saves a lot of time to solve this problem. This problem is a bit more elegant, but this one's a bit more elegant, but harder to understand. But there's ways to get around. So so when your recursion has issues, especially when you need to redo work, think about basically how you can use tail recursion, or think about how you can use an array to store your previous answers, which ties into this technique that you should learn in in algorithms called dynamic programming. So, all right, so that's pretty good for over here. Next time we're going to learn how to search we're going to learn about binary search, and then we're going to learn about the recursive linked list. The practice exam will be, so I should hope to post the practice exam tonight. That's my goal. Practice exam goes up tonight. And if we don't go over it on next Wednesday, then I'll probably post a video where I go over the answers instead. Okay, so I think we totally had a quiz and I forgot about it. So I'll have to send it out to you guys. I'll put it out. I'll send it out. You'll obviously have to take that in lab, so whatever. It's a short one. Actually, what I'll do, I think, is that I will unlock the quiz and let you guys take it. So, okay.
Question. So